Hi, we are on page 3, maybe one of my favorite pages, where you get to play with arrow pushing and a little bit of acid basics. We're going to start by giving the arrow pushing mechanism for this dichlorination reaction in part A. We want to identify the nucleophile and the electrophile. The pi electrons that make up the double bond of this alkene make it nucleophilic. It makes it electron rich. This is where our arrows are going to start. We identify this as a nucleophile. And since each step needs a nucleophile and an electrophile, this chlorine is electrophile kind of by default. But again, that chlorine is the electrophile because of the induced dipole. I say again because I talk about it in lecture. I haven't said that in this video yet, but there's an induced dipole created when the chlorine gets in the proximity of that double bond. So the arrows are very important of where they start and end. Actually, I might zoom in a little bit so you can see that I'm really starting in the middle of this double bond. I want to do that middle of this double bond and ending at one of the chlorines with a clear double-headed arrow. So we just ended at the chlorine, which means chlorine has too many electrons, so it's going to ditch some, and that chlorine-chlorine bond is going to break. And we knew that was going to happen also because of the product that we're looking at. We can see that we have a new carbon-chlorine bond over here, and that the chlorine-chlorine bond broke. Now it's a little more appropriate maybe to put this over here. So then we should have an easier time figuring out nucleophile and electrophile here. Remembering that nucleophile means it's electron rich, and electrophile means it's more electron poor. So sometimes nucleophiles are negatively charged, sometimes electrophiles are positively charged, but not always, as you can see in the first step of this reaction. But in the second step, they are. So we see here in our products, or no, sorry, in our starting material, that this has a negative charge. That's going to be the nucleophile, and this is going to be your electrophile. And we need to make sure we're taking a look at what's different about the starting materials and the products. So we can see here that we have a new carbon-chlorine bond, and there should be a broken carbon-chlorine bond over here. So we're going to start at the chlorine. We're going to end at this carbon. It actually could have worked out to start at the other carbon as well, but either way, we'd have to kick those electrons up. So that's one solution. And again, we could have gone to the other carbon. So if you decided to go all the way over here, just as long as you kick those electrons up, you're fine. And then we move down to a kind of similar problem where instead of the chloronium ion being attacked by another chloride, it's attacked by water. Let's make sure we understand the meaning of the arrows. This first one here from oxygen to carbon means that we have a new carbon-oxygen bond being formed. And this one that goes up to the chlorine means we broke this carbon-chlorine bond. But everything else in the molecule should stay the same, meaning we still have a 6-membered ring, meaning on this carbon on the top, it's still wedged. And the thing that you want to note as well, because of the stereochemistry that's shown here, and you're told to include stereochemistry, that this water molecule had to attack from behind. Or in other words, from the opposite side of the chlorine atom. So we have an oxygen still connected to 2 hydrogens, and to maintain charge balance, we should still have a positive charge, and we see it's there on that oxygen. Next, we're going to add the products of these reactions. These are acid-base problems. This guy here is acetic acid, has a pK of about 5. This is an ammonia derivative. This is a pK of about 35. So this guy's going to be the base. This one here is the acid. You don't need to show arrows, so I'm not going to here, but just to kind of highlight what's happening, that proton is going to be lost, and it's going to be picked up by that nitrogen. So the products that we get here is our first conjugate base, acetate, and the CH3, or rather methyl ammonia, is now methyl ammonium with 3 nitrogens, and nitrogen has a positive charge. Next, we see sulfuric acid is a very strong acid. This alcohol, methanol on the left, it could be a weak acid or a base, but because this is a strong acid by default, this is going to act as a base. More specifically, oxygen lone pair going to pick up one of those protons. So when that happens, we have This oxygen now with 2 protons and a positive charge, and the conjugate base of sulfuric acid is simply bisulfate. Those are the 2 products. Those are the 2 reactions. And then finally, we're at the pKa part. If it makes you feel better to see the actual structures, we can do that. HCl, H2O, hydronium, H3O+, acetic acid is a carboxylic acid, ammonium, NH4+, and ammonia is NH3, methane, CH4. This was just a memorization thing. -7 for the strongest acid. Water is 16. Hydronium is 0. Acetic acid, carboxylic acid is 5. Ammonium's 10. 35 for ammonia. And methane is about 50. That's page 3.